Hello, this is Jack Jackson. In this video, we're going to continue to look at Newton's method. In fact, we're going to review and go back over some things that were in the last video and expand upon that a little bit. So Newton's method is used to find approximations of real zeros of functions. In other words, x-coordinates of the x-intercepts of a graph of a function. And so we do have algebraic techniques for solving certain kinds of equations, like we can solve any linear equation pretty easily, in fact, which is part of what makes Newton's method work. We have the quadratic formula, there's a cubic formula and a quartic formula. There are not formulas for higher degree polynomials than 4. We have some techniques that work on exponential functions and some that work on logarithmic functions, and we know some techniques that work with some functions that have trig functions in them. But it turns out that oftentimes, even if we can find one of these solutions very easily, sometimes the answer is an irrational number. And so it's impossible to find an exact decimal value for it because it never terminates or repeats. And it's maybe extremely difficult to find a decimal approximation for them, particularly without a calculator. And furthermore, there are many types of equations for which there is no method existing for finding exact solutions. And in all of these cases, we're often interested in finding decimal approximations to these solutions. And Newton's method gives us a very powerful technique for finding these approximations. Now, you may also hear Newton's method referred to as the Newton-Raphson method. Newton, of course, who's named after Sir Isaac Newton, one of the developers of calculus, inventors of calculus. He used a special case of this method at least as early as 1669. Some other special cases were known in other places around the world, and a more general method was published in 1685 by John Wallis. Joseph Raphson, the other name in the Newton-Raphson method, published a simplified version in about 1690, and more or less the modern version that we're using here was published in about 1740 by Thomas Simpson. So I guess we could even call it the Newton-Wallis-Raphson-Simpson method, but Newton's method is usually what it's referred to as. So let's illustrate this. This is the same example that I used in the previous video when I had a geometry sketchpad sketch that I looked at. And this is the equation x squared minus 2 equals 0. Of course, we can solve that very easily by hand. X squared equals 2 and x equals plus or minus the square root of 2. But of course, whether you write it as the square root of 2 or maybe 2 to the 1/2 power, that's really the only way you could represent that because it's an irrational number. So if you want a decimal approximation to that, then we need to come up with some method of doing that. Now, of course, we have a button on the calculator, but it sort of begs the question, well, what is the calculator doing to evaluate that? So what we're going to do is we're going to start by graphing it. And here's a graph of the function, a portion of the function, and we're interested in finding the square root of 2, which is this little red, the x-coordinate, this little red dot right here, where the graph crosses the x-axis. Okay, and we want to get a decimal approximation to that. Well, we can certainly see just by looking at this, it's between 1 and 2. In fact, it looks like it's between 1.4 and 1.5 just looking at this graph. So what we start with is we start with a guess. And I'm going to, just for the point of illustrating this, I'm going to make a particularly bad guess. So I'm going to guess way over here where x sub 0 is at 0.8 for my first guess. Suppose we guess that for our first try. Now what we do is we need to find the corresponding y value right here on the graph, which is x sub 0. F of x sub 0 is the point. F of x sub 0 is the y value. And of course we know the formula, so that's pretty easy to do. 2 minus x squared is 2 minus 0.8 squared when x is 0.8, and that works out to be 1.36. Easy enough to do in your head there. So now we have the coordinates to that point. Next, what we want to do is we want to draw the tangent line in here. Okay, well, to find the tangent line, we need to know the slope of the tangent line, which is the value of the derivative. So we use our derivative shortcut rules to say that the derivative of that function, 2 minus x squared, the derivative is negative 2x. So there's the derivative function. And then we evaluate the derivative at that point. It's just 2 times, no, negative 2 times 0.8, which is negative 1.6. So that gives us the slope of the tangent line. And remember, the equation of a line in general is y equals the slope times parentheses minus x minus the x value that we know goes through there, which is 0.8, plus the y value, 1.36. So that's the equation of the tangent line. That's specifically the tangent line to this function at that particular point. More generally, y is f prime at x sub 0 times parentheses x minus x sub 0 plus f of x sub 0, where x sub 0 is our original guess. And so then we can see the tangent line. Now what we want to do is use the idea that the tangent line and the graph are pretty close together, at least for a while. So if we follow the tangent line down, we're more or less kind of following the basic direction of the function down to where it touches the x-axis. That's the basic idea. So we come down and follow that and find out where it crosses the x-axis. Well, what we're doing is we're solving an equation. We have a formula for this line, like you can see it highlighted right there. And what we want is this place where it crosses the x-axis is x1. So it says if you put x1 for x, we put 0 for y because it's on the y-axis. We know y is 0. And we're solving that equation. Being a linear equation, that's very easy to solve. Okay, so here are the details for that. Here's our equation, negative 1.6 x minus 0.8 in parentheses plus 1.36 equals y. If we put in x1 for x, and then we can put in 0 for y. So this should allow us to solve for x1. We can subtract the 1.36 from both sides, and then divide by negative 1.6, and I swap sides, and then add 0.8, and here we have an expression which we can evaluate. And again, this is not too hard to do even by hand. Two negatives cancel, make a positive. 1.36 divided by 1.6, well, that's a little bit of long division, but we could do that. Not too much trouble, and get 0.85. Add it to 0.8 and get 1.65. So far we haven't encountered anything that we couldn't do by hand without a calculator. In general, what does this look like? Well, in general, our formula is y equals f prime at x sub 0 times x minus x sub 0 plus f of x sub 0. And we plug in x1 for x and 0 for y. And we want to solve for x1. So we're going to subtract the f of x sub 0 from both sides, and now switch sides also. Then we're going to divide by f prime of x sub 0, and then we're going to add x sub 0 to both sides. And you see here in the little box an expression that tells us how to find x1 once we know x sub 0. And if you look at that, that's a pretty simple little formula, a little process. What do? We take to find the x1 value right here, what do? We take this x value here minus this y value divided by the derivative, which is the slope there. And that gives you this formula, and that gives us our x1. That'll solve for the x-coordinate right there, that point there. Now the thing is we hope and we maybe expect that x1 should be closer to the point of intersection here that we're looking for, the x-intercept, than x sub 0 is. And you can see that's certainly the case here. Where we started with a really poor guess, so we started way away, and now we got much closer there. Okay, and so now what do we do next? Well, we just want to repeat the process. Pretend now x1 is our guess and repeat the process. So we take x1, we go down to the curve here. That'll be x1 comma f of x1. Find the slope of the tangent line, which is the derivative at x1. Slide along the derivative, graph the tangent line, slide along the tangent line until it hits the x-axis. And you can notice just by looking at it, x0 is out here, x1 was over here to the right, and then x2 is already pretty darn close to that point we're looking for. So we're actually, even by the time we get to x2, we've got a fairly decent approximation, even from a really bad first guess here. Here are the details. So we basically use this same process. So x2 then is just x1 minus f of x1 over f prime of x1, and we just plug in 1.65 is x1, and then 2 minus 1.65 squared is f of x1, which is negative 0.7225. And negative 2 times 1.65 is the derivative there, which is negative 3.3. work all this out, divide these out. Again, we can do that by long division. It turns out to be repeating decimal. 0.2189393939393. And subtract there, we get 1.4310606060606. And so we've achieved x2. Well, guess what? We do x3 the same way. We approximate it by finding the x2, which we just found, and then use this iterative process here. So this basic result that you see right here is basically Newton's method formula. That's a recursive or iterative formula that we can use over and over again to take one guess to get a better one. So if we take the nth guess minus f of x to n and divide it by f prime of x n, then that computation will give me the n plus 1 guess. And then guess what? We do it again and again and again. And we do this as many times as we want to. And each time we should be finding better and better approximations. For our particular one, here's the formula worked into it. And so here I have in the table some of the results, the numerical calculations. So if n is 0, we just start with what are our first guess. This is 0.8. We find the y that goes with that, which is 2 times 0.8 squared, which is 1.36. 2 minus 0.8 squared, which is 1.36. Then we find f prime of n, x sub n, 2 f prime of 0.8, which is negative 2 times 0.8, which is negative 1.6. And then we put in this formula to find x1. Then that one, the output of that becomes the input the next time. That becomes our 1.65. And you can see here how we put that in here in the original formula to get the y value that goes there. We put that in the derivative formula to get the derivative there, put in this formula here. We'd already worked those two out. So let's do another one. So notice this output here becomes the becomes x2, the input the next time. Now, if we start keeping all these digits, the arithmetic starts to getting a little nasty. But I mean, it's still something you could theoretically do by hand, although it's getting a little bit nastier to actually compute. But it's still the same basic setup there, and you can see the details worked out here of the solution, and then we get x3 out of that. And of course that becomes the input the next time, and then here we go, and we get x4, and then we use x4 to get x5, and x5 to get x6, and so forth. As you notice, looking at the numbers in the table, they start to agree pretty soon. So like when you look at these two, we see the 1.4 agrees. So there's a good chance that's actually accurate, at least that far. Then you look at the next two, the 1.414 agrees, so it looks like that's at least accurate. And the next one, they all agree except for the last digit, so those are all accurate. And at least some question about that next to last one. And then we go here, we get that, and down here we see that the output is the same. Well, it's not exactly the same, but to that many digits that I'm keeping here, which is the same number of digits that my calculator will display, we see that the sixth estimate and the fifth estimate are the same. In other words, if we take this estimate right here and actually put it into the function, we sure enough get 0, at least up to many digits, up to as many, at least that many digits. It actually is 0. So this is the number we're looking for, at least up to that many digits. So each successive approximation adds more and more digits, significant digits of accuracy. It turned out that after 2 iterations, our x sub 2, with a particularly bad initial guess, actually, we actually had 2 significant digits. The time we did one more, we did 4 significant digits. The next time we did 1, 2, 3, 4, 5, 6, 7, 8 significant digits. The 6 would actually round off to 7 and would be off by 1. And then we go on down here. So more or less, it looks like we're about doubling, once we get started here with some significant digits, looks like we're about doubling the number of significant digits each time. Okay, so at least in this particular, for this particular function. So this actually gets us a very quickly is going to give us lots and lots of accuracy. Now all of the calculations that I've done here could be done by hand, although they start getting pretty tedious once we start keeping this many significant digits in our answers. And let's see, what can we do? Well, if we have computers or calculators, then we have the ability to do some more things. Of course, back in the 17th, 18th, 19th centuries, they didn't have calculators. So, Newton and Raphson and those guys, this is how they would have had to have done this, and they would have had to do all these calculations by hand. But now we have calculators. So let's take a look at how we can do this on a calculator. Okay, so let's start with the TI-84 calculator, and let's start by putting in the original formula in the calculator. So you hit your y equals key and you type in the formula, 2 minus x squared, and go ahead and put the derivative in the next one here, which is opposite of 2x. Okay, there we go. And we could graph it if we want. Let's just start with maybe a zoom standard. And we clearly see that there are two places it crosses the x-axis. This is the derivative being graphed here as well. But we're interested right in here for that particular one. There's also one over here which is just the same number with the opposite sign. Same absolute value with the opposite sign. Okay. So what we want to do is do this. We start with our first guess. Okay. And our first guess was 0.8. And I'm going to take this 0.8 now, and I'm going to actually store it as x. Now here's your store key, STO. Store it as x. Okay, now what we want to do is we want to take x, that x value, which is, when I type x, it'll give me the 0.8, minus f of that. Well, f of x is in y1, so I can hit variables, go to y variables, function, y1, of that x value. But I'm going to divide that by the derivative of y1, derivative of f of x, which is in y2. So that's variables, y variables, function number 2, y2, of that x value. Now I'm going to do something kind of interesting. I want to take that and store it as x. Now when I hit enter, notice it did the calculation. That's 1.65. Same thing we got up here in the table when we did it by hand. Okay, now let me show you something really slick. If I just hit enter, it's going to execute this previous line. But since I stored this as x, it's going to execute this line with 1.65 in place of x instead. And so we get this second, let's look at the table here. We got this next approximation. And if I hit enter again, we get the next approximation here. And just hit enter again, we get the next one. And get the next one here. And if we hit enter one more time, we got the same thing twice, so we know we're as far as we can go on our calculator. Now, isn't that slick? It's just an iterative process, and you just keep running this till these basically don't show any difference, or until the function evaluates to 0 to a certain number of places, which are basically going to give you the same thing. Okay? And so that's a pretty slick little thing, and a very easy way to do that in a graphing calculator. Okay? Now it turns out I had a really bad guess, but if I'd have were to put in something better, here I put in 1.5, but looking at the graph, it looks like maybe 1.4 was a better guess. If I had started with 1.4 as my guess, let me do second enter till I find keep doing second enter till it cycles back. There's my Newton's method formula, basically. then actually this converges very quickly. And then after 1, 2, 3 iterations, we had it as far as the calculator would go. So pretty slick. Here I did it with 1.5 as my guess. Now, so notice that this does require us to put in the original function in y1 and the derivative in y2, so we have to be able to find the derivative formula to do that. Or do we? Wait a minute. What else could we put in y2 instead? Well, this is an approximation method anyway. Why don't we use MathA, which is a numerical derivative of y1 with respect to x, evaluated an arbitrary x, and that's the derivative function. Well, not really. It's actually a symmetric difference quotient, but it approximates the derivative very nicely. And so I can use this in place of that. And notice again, let's just say I start with 1 this time as my initial guess. And then I want to basically use that same formula. This time y2 is not the actual derivative, but the numerical derivative. You'll still get there very quickly after 1, 2, 3, 4 iterations. You got there as far as the calculator would go. And so we can actually use that. Use a numerical derivative and not actually have to know what the derivative formula is. Now there's some advantages to actually having the actual derivative formula in there, but that's one way to do it. Okay, and where we don't even have to find the derivative. Now let's go back to just look at the original function. Now, one of the things that happens is the guys that made your calculator know about Newton's method. Okay, and basically they have it built into the calculator already. So I can go here and tell it to calculate a 0, which is second trace, which is calc. And I want to go down to number 2, calc a 0, and it asks for a left bound, so I get close to the curve, to the point where we're looking for, but not on it, and hit enter. Asks for a right bound, make sure you're on the other side of it, hit enter. And then it asks for a guess. What are we doing here for the guess? We're giving it that's our x sub 0 that we're giving it. And what's it going to do? It's going to do Newton's method, or at least something very, very similar to Newton's method. And so it's going to give us a y of 0 and an x value there. Sometimes it will give you a y that's almost 0, but this should be pretty accurate. Now it also takes this value and stores it as x. So if I quit and just type in x, it will be the value that we just did. Similarly, if I do alpha y, of course, it'll be what y just was, which is 0. So actually, Newton's method is really built into your calculator already. Pretty slick. Okay, so here's an exercise for you to do. Use Newton's method in a calculator to approximate pi to the limits of your calculator. And the way we're going to do that is we know that one of the solutions to one of the roots or zeros of f of x equals sine of x is pi, one of the zeros there. So if you plug in x equals pi, this will give you 0 for y. So use that idea to come up with a solution, a decimal approximation pi, but use Newton's method to do it. Okay, so here's what we do is we let y1 be sine of x, we let y2 be the derivative of sine x, which is cosine x, or we could just leave it the numerical derivative. And again, we seed it with the first guess. We know pi is approximately 3, so I could say 3 stores x as my first guess. And then say x minus y1 of x divided by y2 of x and store that back in x. And just repeat that over and over again until we don't see a change. And so we see pi is approximately 3.141592654. Okay? Tell you what, let's stop here and we'll see in the next video or two how we can do some other things with Newton's method to do some other things like finding intersections, solving equations, finding inflection points, and max and mins and stuff. We'll look at that in a minute.